So in today's video, we are going to talk about binary search pattern, which is not so obvious if you are new to binary search. So we can also say that this is an intermediate to advanced binary search pattern. So let's take a look at this question. Maximum candies allocated to k children. I would suggest pause this video and then read through the questions. So the question says that we are given a zero indexed integer array candies. Each element in the array denotes a pile of candies. Okay, so there is an array of candies and candies I, each value in candies array is a pile of candies. It says that you can divide each pile into any number of sub piles. Okay, so for example, this one, so one of the pile is 5, so we can divide it into a smaller, like smaller piles of any size. Okay, but we cannot merge into, it says that you cannot merge into, okay, piles together. You're also given an integer k. You should allocate piles of candies to k children, and then once we have those piles, we have to allocate piles of candies to k children such that each child gets the same number of candies. Okay, so let's walk through this example and try to understand the question more deeply. So the pile given to us in this first question is 5, 8 and 6, right? And k is 3, so this is basically the number of children that we have to divide these chocolate piles. Okay, now the condition is that each child should get equal number of chocolates. So it says that there are 3 children to which we have to allocate these chocolates. Okay, and each chocolate would be allocated to each chocolate pile would be allocated to 1 children. Okay, so this is important. Pile children, so there is one-to-one relation, and then it says that all the children must get equal number of chocolates. So whatever pile we assign to each of those children, that those piles should contain equal number of chocolates. So if you see, like right now these piles are not equal. Okay, our task is to like divide these piles into whatever number we prefer, such that each children get equal number of chocolates. Okay, it all, and we have to, what we have to do is we have to return the maximum number of candies each child can get. Okay, and by doing so we also have to like kind of maximize the number of child. So if you see, like if we, so let's try to run through this. Let's say I say that I am dividing this piles or candies of chocolates into pile size 1. Okay, then how many piles would be there, right? This would be broken down into like 5 piles. Similarly, like this 8 would be broken down into 8, and then similarly this 6 would be broken down into 6 chocolate piles, right? So 5 plus 8 plus 6, which is 19, right? So we would have 19 piles of chocolate. Each pile would contain 1 chocolate, and we have 3 children, so we could assign like each 1 pile to each children. Each children would get 1 chocolate, right? But it says that we have to divide, we have to create the piles in such a way so that the maximum number of candies are allocated. Okay, so what we can do is, in another approach, like we can say, okay, let's take pile size of 2. Okay, and then let's see. So 5 could be divided into how much? 2 and 2 and 1, right? 8 could be divided into 2, 2, 2, 2. 6 could be divided into 3 piles of size 2. Okay, now let's see, now how many piles we have? 1 2 3 4 5 6 7 8 9 10 piles. Okay, but we can assign like each pile of size 2 to each children, but again, is this the maximum? That is the question. Okay, so you see like how we can solve this. So now coming back to the patterns of questions, like these kind of questions would have a pattern where we would be given some constraint, and it has to be like, so the question would be something like, given some constraint, like it has to be greater than some value. So for example, in this case here, this is the constraint that we have to divide the piles into k, like k children's, right? So there should be at least like k piles of equal size, right? That is the constraint, and given that constraint we have to maximize some value. So So this is also called a min max pattern. So there would be some constraint which we have to minimize or maximize, and based on that we have to kind of fetch the results. Okay, so for example in this case we have to kind of maximize the chocolate, the pile size, number of chocolates in piles. Okay, and given the our constraint is that there should be at least k piles. Okay, so let's if you think about like if you've never seen this problem, what you could do is like you could continue like this, start with pile size of 1, then 2, then 3. Okay, let's see what happens when we take 3. Okay, so 5, 8 and 6, right? So 5 would be divided into 3 and 2, right? 8 would be divided into 3 plus 3 plus 2, right? And 6 would be divided into 3 plus 3, right? So now how many piles we have? This is 2, 2 and then plus 3 and then 2, 8 piles, right? Or 7 piles, 7 piles. But so we can easily distribute like among 3, right? So 7 is definitely greater than equal to k, so we are good, like we have sufficient piles. And you can see like we can assign these size 3 piles to each of the children, and that would like form one of the solution. But we have to maximize this, the number of chocolates, right? So what we can do, we can again say, okay, let's try to create a pile size of 4. Okay, and then let's see what happens. So if you do that similarly, you would find the answer, which is 5, right? So also another important thing to notice here is that in like trivial binary search questions, the array given is sorted, but here it's nothing like that, right? But if you notice the search space that we are traversing, that is linear, right? So we are doing a linear search, right? And we are incrementing kind of our search value, right? So what is our approach? We would start with a pile size of 1, and we would see if that satisfies our condition and how many chocolates each children would get, right? In the next iteration we would increase the pile size, okay, and so on. So we are kind of doing a linear search. Okay, whenever you find a question like this, try and you come up with first solution that is kind of a linear search. That is your cue to kind of optimize it to a binary search. So moving to binary search from this from here is like easy, right? So we have, so for binary search we have to kind of come up with a range, okay, b, e, okay, and then we would search. So we, instead of like incrementing, like starting from 1 and incrementing the pile size by value 1 in each iteration, what we would do it, we would do binary search. Like we would start from a minimum mid value and then we would see what would be our conditions and all. Okay, so what would be b in this case? Like the b would be like the minimum pile size, right? So we can take it as 1, right? And what would be e? So e could be like the maximum value present in the candies array, right? Why? Because we cannot create any pile greater than that value, right? So it's a good enough assumption for us. So that would be like max of candies I. Okay, and then we would start with a m, and when we would pick a m, that is, we would in the binary search, like we would do this b plus e by 2, and then when we get this m value, we would try to satisfy our condition. With this m, we have to see how many chocolate piles we can create. Okay, so for example in this case, like taking this example of 5, 8, 6, our b value would be 1, e value would be 8, right? So m for the first iteration would be 4, right? So we started with 4. Now with 4 we would see how many piles we can create. So for 5 we can divide it into pile of 4 and 1, right? 8 we would divide it into 4 plus 4, and 6 we could divide into 4 plus 2, and we could use these 3 piles to allocate to k children, right? But you see, like we are already satisfying the condition. So number of piles created are still more than k, right? So whenever we are to optimize, what we can do is, what would be the condition? We see here that the number of piles created is more than k, right? So number of piles of size 4 are 4 here, right? But we have only 3 children. So this means that there could be a further optimization, like since we have to optimize the number of chocolates in each pile, what we could do is we could like, since we are still creating more number of piles than required, what we could do is we could try to increase the number of chocolates in each pile. Okay, so what we could do is in the next value, what we would do is like we would say, okay, let's set my b to 4, okay, and e to whatever is the value, 8, and then let's see if we can increase it. Okay, so that way is like we would arrive at a solution. Okay, so let's see the code for it. Okay, so here is the code for the maximum candy solution in Java. Okay, so let's just go through the code once. So here in this line I am just setting b and e, okay, and here I am just finding out the maximum of the array in big O of n. Okay, now this is my loop for binary search. Okay, I'm saying like while b is less than equal to e, and then it's pretty trivial, right? So I'm calculating m, and then here in these two lines I'm trying to calculate how many number of piles I am able to create with this m value. Okay, and then here I'm saying that if the number of piles created are more than equal to k, then next time I'm going to increase the number of chocolates in each pile, and then this would iterate again, and then when the loop breaks, e would be at our optimal value. Okay, so you could run this code and then that would work. Let's move on to another question. So here is another question on the similar pattern, Coco eating bananas. Okay, so again it says, you can pause the video here and go through the question. So it says Coco loves to eat bananas. There are n piles of bananas. The ith pile has piles I bananas. The guards have gone and come back in h hours. Okay, Coco can decide her bananas per hour eating speed of k. Okay, so, and this is what we have to find. Okay, bananas per hour eating speed. Each hour she chooses some pile of bananas and eats k bananas from that pile. Okay, and it says that if the pile is less than k bananas, she eats all of them instead and will not eat any more bananas during the hour. So Coco likes to eat slowly but still wants to finish eating all the bananas before the guards return. So again we have to return the minimum integer k such that she can eat all the bananas within h hours. Okay, so again if you look at the problem statement, it fits our pattern. Okay, so here our constraint is that we have to finish, like she has to finish within h hours. Okay, so constraint is like we have to satisfy some value which is less than equal to h, and then also we have to like minimize based on this. Okay, minimize the value of k. So we could really choose a like big value, and then she could finish the piles fast, right? But we have to minimize this. Why? Because Coco likes to eat slowly. Okay, so let's take this example. The first one, 3, 6, 7 and 11. Okay, so 3, 6, 7 and 11, right? This is the pile of bananas. So if you take a look, if I choose the speed of k equals 11, like she could finish in 4 hours, right? And h given is 8, so maximum time given is 8, but she could finish in 4 hours only, right? But that is not our goal. We have to minimize this value, right? We have to minimize k. Okay, satisfying h, like the number of hours still needed should be less than, like this is the upper bound on the number of hours. Okay, so again what could you do? Like what could be the first solution that you can think of? This is again a search problem, right? What we could do is like we could say, okay, let's say k is 1. Okay, and then what we would do is we would find h, like number of hours needed by Coco. If it's h, so how many she would take? In this case, like 3 for here, 6 plus 3 9, 7 16, and then 27 hours, right? So which is greater than h given, which is 8, right? So what we have to do is we have to increase the rate of eating. So we could linearly also increase to 2. Okay, what happens with 2? How many hours Coco will take? So for 3 she would take 2 hours, right? So 2 and right, yeah, 6 she would take 3 hours. For 7 she would take 4 hours, and for 11 she would take 6 hours, right? So in total 15 hours. Still it is greater than 8, so we have to again increase, right? So that ways, like we have to minimize the number of minimize k such that she finishes all the bananas within h hours. Okay, so again, if you see like this is our search space, and this search space is linear, right? Like this is sorted, right? So if this is sorted, we have to find the range in which we want to do the search. Okay, and then we could just start with a binary search. Okay, so again, b could be 1, right? And what would be our max value? Like what would we do? Again, similar to previous, like the max speed could be like this one, right? Because if we choose max speed more than this, that is of no use. That is similar to this one. So, and that would increase the search space, which would increase the runtime, right? So this is a fair enough value to start with for maximum value, so which is 11 here, right? So now in this case 1 and 11, and then we would calculate m, and we would do a similar thing like a binary search. Okay, so let's take a look at the code and try to understand. Okay, so this is the code that I have written for the same problem. So again, as I explained here in this line, what we are doing is we are setting L and R. Okay, and then what we are doing is, like, we are here in this line, like this is our loop for binary search. Okay, and what we are doing is, here I am just calculating m. So we have to be careful while calculating m. Like all those basic concepts have been covered in the binary search part 1 video. If you have not seen it, go take a look. It contains some useful information. Now based on that, what I'm trying to do is I'm trying to calculate what is the number of what is the number of hours that Coco will take with this rate. Okay, so p piles, the logic is simple. Like I'm just dividing, and if there's anything remaining, then I'm adding one more hour. Now if this is less than h, then what I have to do, I have to increase, right? I have to kind of decrease the rate of eating, yeah, because Coco finished too fast. So R would be set to m, otherwise L is set to m plus 1. And then when this binary search loop breaks, L would contain our answer. So these are the two examples that we would see today in this video. A question on the similar pattern was asked very recently in the weekly contest. And that question is like, we have already posted the explanation for that in one of our videos. But this is that question, house robber 4. So I would suggest, if you have not seen this question, go through this, try to solve it. If not, then I would link the explanation video. You could go through this and understand, and let me know if you have any questions. Stay tuned for more videos on data structures and algorithms, and thanks for watching.